Hello everyone. My name is Azara. I am a student of Information Systems, Faculty of Mathematics and Natural Sciences at Samrajalandji University. In this video, we will discuss graph theory and book embedding with Professor Wilson.
Good morning everyone. I am Professor Wilson. And today, I will give you a very interesting material about graph theory and book embedding.
Graph theory sounds complicated. What is it actually?
Great question. Graph theory is a field of mathematics that studies graphs, structures made up of vertices or nodes, and the edges that connect them. It is used to model relationships, such as cities connected by roads, or people connected through social networks. There are several types of graphs in graph theory, and each has a different purpose, depending on the situation you want to model. Let's start with undirected graphs. In this type of graph, the edges have no direction. That means the relationship between two nodes goes both ways. For example, think about friendship. If you're friends with someone, the relationship is mutual. So, if node A is connected to node B, you can go from A to B and also from B to A without any restrictions. Next, we have directed graphs, also called digraphs. Here, the edges have a specific direction, like arrows. This is useful when the relationship is one way. For example, on social media, when you follow someone but they don't follow you back. In graph terms, that would be an edge from you to them, but not necessarily from them to you. Then, there are weighted graphs. In these graphs, the edges are labeled with values or weights that often represent cost, distance, or time. Imagine a map where each road between two cities has a number indicating how many kilometers it takes. That number is its weight. Weighted graphs are very useful in problems like finding the shortest path or calculating the most efficient route. Finally, we have the complete graph. A complete graph is one where every single vertex is connected to every other vertex. No one is left out. For a graph with n vertices, this means there are exactly n1/2 edges. Complete graphs are dense and highly interconnected, and while they're not always practical in real-world systems, they're very important in theoretical studies. Each of these types of graphs helps us visualize and solve different kinds of problems in computing, engineering, transportation, and even social sciences.
Oh, I see. Now I get it. So where is the book embedding?
Okay, now we get to the fun part. Book embedding is a way of drawing a graph by placing all of its vertices, nodes, along a straight line, called the spine, and then drawing edges in the areas above or below the spine, called pages. The goal is to make sure that no two edges on the same page ever intersect. Imagine taking all of the vertices of the graph and placing them in a straight line, like placing them along the spine of a book. Then we draw edges on the pages, the areas around the spine of the book, so that no two edges on the same page ever intersect.
So, is that useful for anything in the real world?
Absolutely. It's used in circuit board design, network visualization, instruction scheduling and compilers, and organizing data structures more efficiently.
So how do we know how many pages a graph needs?
That's called the page number or book thickness. It's the minimum number of pages needed to draw the graph without any edge crossings per page. For example, a path graph, which is just a sequence of vertices connected in a straight line, like 1-2-3-4 can be easily embedded on one page. Since each vertex is only connected to its immediate neighbors, the edges can be drawn without any crossings, simply above the spine. This makes it a perfect fit for a one-page book embedding. Next, a cycle graph is quite similar to a path graph, but with one extra edge that connects the last vertex back to the first, forming a closed loop. Even with this additional edge, we can still draw all edges on a single page without any overlaps, as long as we arrange the vertices carefully and arc the final edge over the top. So yes, a cycle graph also fits nicely on one page. However, things become more complicated with a complete graph, especially K5, a graph where every vertex is connected to every other vertex. With 5 vertices, that means 10 edges in total. It's impossible to draw all 10 edges on a single page without some of them crossing. Even with clever arrangement, we would still need at least 3 separate pages to draw all edges cleanly, with no intersections on the same page. This example clearly shows how the complexity of the graph affects the number of pages needed in a book embedding.
So more complex graphs need more pages?
Exactly. And finding the right vertex order on the spine is the tricky part. It's like solving a puzzle. So, to sum it all up, graph theory gives us a powerful way to represent and analyze relationships between objects, whether it's computers in a network, cities on a map, or even people in a social group. We explored different kinds of graphs: undirected, directed, weighted, and complete, each suited for different real-world problems. Then we learned about book embedding, a method of organizing graphs in a neat, readable way by placing all the vertices along a central line, or spine, and assigning edges to different pages to avoid crossings. Simple graphs, like paths and cycles, can often fit on just one page. But more complex graphs, like complete graphs, may require multiple pages to maintain clarity. Understanding how to represent graphs efficiently, both visually and structurally, is key to solving complex problems in computer science, mathematics, and beyond.
Wow. So book embedding is like organizing chaos into order.
Exactly. And that's the beauty of graph theory. It helps us find structure in the most unexpected places.
Thank you, Professor. I never realized how much depth and structure there is in something as simple as dots and lines. Now I see graphs everywhere, in social media, transportation, even my daily tasks. I'm excited to learn more and see how I can apply this knowledge in real-world problems. Graph theory isn't just theory. It's a whole new way to see the world.
I'm glad you think so. See you in the next class.
Definitely, Professor. Thanks for the great lesson. See you in the class.